All right, hello students. Welcome back to another video lecture for ComSci 137, Data Communications and Networking. So last time we were talking about line coding and we discussed the different line coding techniques shown here. And this is a summary of the different characteristics. Normally, we focus on the bandwidth requirement as well as some of the desirable characteristics for encoding, like the absence of DC component, self-synchronization, etc. Now, we will continue with the block coding. So block coding, we want to make our signal, we want to provide redundancy to our signals, and we can do this by, in order to provide synchronization and error detection. So remember that synchronization is also important in the digital to digital encoding, because this will allow the receiver to properly interpret the signal received. Okay. So in block coding, what is done is it changes a block of M bits into a block of N bits, where N is greater than M. The notation is MB/NB. So you might think of this as very similar to the multi-level scheme, but this is a different approach. So in the block coding, we have division, substitution, and combination steps. And in this discussion, we're going to look at 4B/5B and 8B/10B. So this is how block coding works. We have this original bit stream. This will be divided into M bits, and there is a substitution step wherein these M bits are converted to N bits, and this is what will be sent across the line, the N bit stream. So that's basically the idea. So the interesting question is, how do you map these M bits to these N bits? So you need to provide a mapping function or substitution function to do this. And usually the 4B, 5B, so this is the M, this is N, right, is combined with NRZI, non-return to zero, inverted, before it is transferred or transmitted across the link. So the idea here is NRZ. If we look back at the characteristics of NRZ, there is a problem with long zero. So remember that if you have a sequence of long zeros or long ones, the receiver will lose timing and misinterpret the bits. So as much as possible, we don't want long sequences of zeros or ones for a given signal. So this is what is accomplished here in NRZI. So by using this blocking scheme, we will prevent long sequences of zeros or ones. So this is the mapping table that I was mentioning, or the substitution function I was mentioning a while ago. So if we have 4 bits, so these are all the possible combinations of the bit pattern, possible combination of the bit pattern, and they will be mapped to a 5-bit sequence. So this is 5 bits, this is 4 bits. So you will notice that, for example, this long sequence of ones and zeros will be encoded as 11110. Okay. So obviously the 5-bit block will have more combinations, so some bit patterns will be treated as control sequences, meaning they do not encode actual bit values, but rather they represent control information. Okay, so that's for the 4B/5B. So I did not show the 8B, 10B, but it's the same. So 8 bits will be encoded into 10 bits. So the last technique is called scrambling. Okay? So in the scrambling technique, the bipolar AMI, alternate mark inversion, is most suitable for long distance transmission. Why? It has narrow bandwidth and no DC component. So if you look back at the summary, bipolar AMI, it has a bandwidth which is lesser than the bandwidth of biphase, and the problem is we need to have signal with no DC component. Okay. So those are the ideal characteristics for long distance communication: narrow bandwidth and no DC component. But the long sequence of zeros actually will disrupt synchronization. So the solution is to substitute long sequences of zeros with a combination of other levels. Okay? And this is accomplished by scrambling, wherein we have two techniques, B8ZS and HTB3. Right? So how does scrambling technique works? Okay. So let's start with B8ZS. So in the bipolar with 8-0 substitution, what it does here, 8 consecutive zero-level voltages are replaced by a sequence of this bit pattern. Okay, so let's say the sender will detected that it has to send, let's say, a color black. So the color black is represented by all zeros, for example. Before that all zeros is transmitted to the line, to the wire, it will be converted into this pattern. Okay, so 00V and VB, 0VB, where V is a non-zero voltage violating the alternate mark inversion rule, and B is a bipolar non-zero voltage, which is actually the opposite of V. Okay? So it does not, given this approach, okay, so bipolar 8-0 substitution, it does not change the bit rate. It balances positive and negative voltages, and the substitution may change the polarity of A1. Okay. So let's see how this works. So we have here a sequence of 8 zeros, and we check if the previous level is positive. So the previous level is positive, so we replace that pattern with 00V, which is a violation. So if there is no violation, the correct signal to use should be like this. However, since we have to introduce a violation, So we put it like this, and then we use bipolar, so we use the signal, then we go back. Okay, so this is VB, the first part, and then as shown in this bit pattern, so you should also have a violation. So supposedly this should be up here, but since we need to introduce a violation, we put it down, and then we get this. So the same with this example. So again, we are given a sequence of zeros, and if the previous level is negative, so 0, 0, 0, violation. So if there is no violation, the signal should be here. But since we have to introduce a violation, we put it down here and then put it be here. So the same with the other one. So supposedly it should be down here, but we need to introduce a violation, so put it here and then. So this is the bit pattern that will be sent across the link to represent this long sequence of zeros. Okay, the next scrambling technique is called HDB3, high density bipolar 3 zeros. What it does is 4 consecutive zero level voltages are replaced with a sequence of 00V or B00V. So why 2 sequences? To maintain the even number of non-zero pulses after each substitution. So that's the purpose of having 2 sequences. So what are the rules? If the number of non-zero pulses after the last substitution is odd, we use 00V. If the number of pulses after the last substitution is even, we use B00V. Okay. So let's take a look. So assuming that we have even, okay. So here we have the number of non-zero pulses after the last substitution is even. So we have, let's say, 1, 2 non-zero pulses after the last substitution. Okay. So it's even. So if we're going to use the B00V pattern. So so this is the last pulse. So normal bipolar, and then 0, 0, and then we introduce a violation. So next, at this point, still even, okay. And then so no, but we have no sequence of zeros, so we move here. So we have a sequence of zeros. So what is the number of non-zero pulses? Non-zero pulses after the last substitution. This is the last substitution. The number of non-zero pulses is only one here, so it's odd. So we're going to use the 0, 0, 0, and then violation here. Okay. Then we have a sequence of zeros again here, right after the previous sequence of zeros. So we have 0 non-zero pulses. So 0 is even. So we have bipolar 0, 0 violation. So this is the bit pattern that will be sent. Okay. So that's it. That's HDB3. Okay. So at this point, again, to summarize, so we have for the digital to digital conversion, we have line coding techniques, we have blocking techniques, and we have scrambling techniques. right? So remember that digital signals can be used for both uh, short distance or long distance communication, and we need to have the appropriate properties for the encoding technique if you want, let's say if you want to use the encoding technique for long distance communication or for short distance communication. So that concludes our discussion on digital data to digital signal encoding. Now we're going to look into analog to digital conversion. Okay. So the idea here is, let's say you want to record something, say you're an artist, and of course your voice or your song will need to be recorded to a computer, which is a digital device. So there should be a way to convert the voice, which is an analog signal, to analog data to a digital signal that can be stored on a disk file, like an MP3 or like whatever file format, audio format, MIDI format, for example. Right? So the technique of converting analog data to digital signal is called digitization. So for example, you have a digital camera. If you are familiar with analog camera, you usually have a film. So when you take a picture of a scenery, the data will be captured in a film, and then the film needs to be developed. With the advent of digital cameras, when you take a picture of a scene, the picture is actually converted into image formats or digital data. Okay, so that's called digitization. And in this section, we're going to look at two techniques called pulse code modulation, and the other one is delta modulation. So first let's talk about pulse code modulation. How does it work? So on the left we have the analog data. So let's say this is the voice, and then the encoder will perform three steps. First, sampling; second, quantizing; and the third step, encoding, which eventually will emit the corresponding bits digital data, bit pattern for this analog data. So after the output after sampling is called the PAM signal, and then after the quantizing we have the quantized signal. So let's talk about the first step. The first step is sampling, or pulse amplitude modulation. So the idea here is the analog signal is sampled. When you say sampled, it's detected, right? So it's detected within a certain time period, T sub s, called the sampling period. So recall our discussion about period and frequencies. So in sampling, the analog signal is detected or interpreted at given intervals called sampling period. So the sampling can be ideal, natural, or flat top. The result of the sampling is still an analog signal with non-integral values. So for example, we have the ideal sampling. So this is the sampling period. So at this point, you get the value of the amplitude, you get the value of the amplitude at this point, and at this point, this point. So you have to specify the sampling period. So this is the ideal sampling. Then, so you get certain points. In the natural sampling, so you actually have a somehow an image like this, okay, which is the natural sampling. And then we have the flat top sampling. So wherein we do not trace the exact path of the signal, but rather we create some approximation, some boxes or rectangles to represent the amplitude of the signal. So those are the examples. Now we are given a sampling period. So from that we need also to specify what we call the sampling rate, and the sampling rate must be at least twice the frequency in the original signal. So in order to recover the actual analog data from a digitally sampled analog signal or data, the sampling rate must be twice the highest frequency in the original signal. So remember that every signal has a bandwidth like this, for example. So we have the F min and we have F max here. So twice the highest frequency. So the rate of sampling should be twice of F max. If we have with the zero component, then it will just be twice that F max. But if we don't have, it will be F max minus F min. So I think that's the value. So this is the sampling rate. So the ideal is the sampling rate should be twice the highest frequency to somehow approximate the actual signal. So you sample at this point, at this point, at this point, this point, at this point. So you have this wave. Now if you have an oversampling, so this will be what you'll get, because you sample four times the original frequency, and for undersampling, you get these points here. So you will notice that if you increase the sampling rate, of course you're going to get more sampling points. Okay? So for this one here, you have the sampling points, then the sampling points, and the very few sampling points. So the idea is the minimum, if you have more samples, the better, of course, but it will require some more complexity. But if we have at least twice the original frequency, twice the highest frequency, actually the highest frequency, then it is enough to be able to recover the original signal. So that is sampling. So that's the first step. So the result of that is the palm signal. So the next step is quantizing or quantization. So we assume the original signal has instantaneous amplitudes. Okay, so between Vmin and Vmax. Then we divide the range into L zones, each of height delta, wherein delta equals Vmax minus Vmin divided by L, the number of zones. Then we assign quantized values of 0 to L minus 1 to the midpoint of each zone. Then we approximate the value of the sample amplitude to the quantized values. So let's see how this works. So we are given, let's say, a minimum voltage amplitude of -20 and a maximum voltage of 20, and we have number of zones, 8 zones, Therefore, we can derive D as 40 divided by, this is 20 minus 20, so that will be 40 divided by 8, so we'll have 5. So delta will be 5. So we're going to use that to divide the zones. And this is what we're going to get. So we have 8 zones, and we have this plot here. So this is the time, this is the normalized amplitude. So we have we specify, let's say 0 here, 1 2 3 4 5 6 7, which is the midpoint here. So each of this will be 5. Okay. So indicated in the plot is the actual amplitude. So this is the actual amplitude at the sampling point. Okay. So we have here the normalized PAM values. So this will be minus 22 here, okay, minus 1.22. This will be 1.5. So remember that, okay, our delta is 5. So we're actually trying to map that here. So we have these normalized values, okay, and then we have here the second row, the normalized quantized value. So we get 1.5 here, 1.5 here, 3.4. So we subtract the centers here, or the values here, okay. So each of this is 5. The width is 5, okay. And then we get the error. So these are called the errors, okay. And then to get the actual value of the signal, so let's say this one here, this will be 2, okay. So this one here will be 5, okay. And this one here will be 7, and this one here also 7, etc., etc. And for the analog signal, this will be the digital equivalent, okay, of these points. So when saved, if this is your voice waveform, for example, when you save it to this will be the beat pattern. Okay, so D here is delta, okay? Delta, twice the delta, thrice the delta, 4 times the delta. Okay, so that's pulse code modulation. So after this, we're now going to encode. So each sample can be changed to the n sub b bit code word. The number of bits for each sample is determined from the number of quantization levels. So if the number of quantization levels is L, the number of bits is n equals log L to the base 2. So since we have 8 quantization levels here, we'll have 3 bits to represent each code. So an example is, what is the bit rate needed to digitize human voice assuming 8 bits per sample? Okay. So first we need to compute the sampling rate. Recall that the bandwidth of human voice is between 0 to 4 kilohertz. So what we do is we multiply 4,000 by 2. We said that the sampling rate should be twice the highest frequency. So remember this plot, if we have a voice sound, this will be 4K, 4K Hz, 4 kilohertz. So the required sampling rate should be twice, at least twice. So we have 2 times 4,000, so we'll have 8,000 samples per second, and we multiply that by the number of bits. So 8,000 times 800 times 8, so that will give us 64 kbps. So this means that in order to save your voice to the computer, when you record something, you will need at least a bit rate of 64 kilobits per second. And the bandwidth required is the number of bits, right, times the bandwidth of the original analog signal. So the bandwidth required here, for example, so if we have 8 bits and the original bandwidth is 4 kilohertz, therefore the bandwidth required for this is 32 kilohertz. Okay, so that's what we mean by that. Now at the receiver end, we have a decoder, and the decoder will do the opposite step. So what will come in from the decoder is the digital data, and then it will do some sampling also, and then it will reconstruct the waveform, and then it will be passed to a low pass filter to eventually get the original sound signal. Or an example is the analog signal. So when you play back your recorded voice, this is what will happen. So we have a PCM, we have a decoder. So decoder. So we usually call this a codec, right? For example, you cannot play or record a certain format unless you have a codec installed. Okay. So during the early days, there are even today we have several encoding techniques. So we have codecs for different file formats, for example. So the next analog to digital conversion or encoding technique is called delta modulation. Compared to the PCM, it finds the value of the signal amplitude for each sample. However, in delta modulation, it only finds the change from the previous sample. So this is an illustration of that. So there are actually two waveforms here. So there is actually a staircase waveform here and the actual signal. So what it does is to compare this point here with some points with the values on the staircase wave, okay? And then if it is positive, then we get 1. If it is not, so we get a 0. So there is a certain threshold used. So this is free flowing. So it simply examines the intensity or the change of the amplitude from the previous signal. So that is delta modulation. So you will notice that somehow delta modulation is faster because it requires fewer steps, but of course there will also be some form of errors. Okay, so that's it for delta modulation. So we have this component. So we have a staircase maker. So the staircase maker is the one that generates this staircase signal, and then this is the analog signal. So we have the staircase maker, and then we have a form of delay unit, and then simply compare that the signal with the staircase maker, which adjust from time to time to generate the digital data. For the demodulation, so at the receiver end you'll have an incoming digital data, and then again this will be as input to the staircase maker, and then it will be passed to a low pass filter to get the analog signal back. Okay, so that's delta modulation, demodulation technique. Okay, so we now move on to the last section of this chapter, which is transmission modes. Okay. So the idea of transmission modes is how do you send bits. Okay, so the previous sections talked about the conversion from either digital or analog data to digital signals, digital signals, and these digital signals represent bits. How do you send these bits now? So there are two approaches, main approaches. We have parallel and serial. And under serial, we have three: asynchronous, synchronous, and isochronous. So we will discuss each of these transmission modes. Now, in parallel transmission, we have n wires to send n bits of data. So basically, what we do here is one line or one wire would represent 1 bit. So in parallel transmission, so we have, for example, here we have 8 lines that will allow us to send 8 bits, okay? 8 bits simultaneously in one shot, here in one cycle. So the advantage of this is it's fast, okay? Because let's say these 8 bits represent a character, then in one shot that character can be processed at the receiver end already. So that's called parallel transmission. So most transmission nowadays are parallel transmission, but of course you will need additional circuitry. So usually this is done inside the computer, the buses inside the processor. Okay, they use parallel transmission. So basically you have parallel wires. So for example, you have the memory bus, okay, or the data bus, okay. So it uses parallel transmission. Now for the serial transmission, you only need one wire, and you send the bits that represent information one character at a time. So here we are sending 0, 1, 1, 0, 0, 0, 1, 0. So 0, 1, 1, 0, 0, 0, 1, 0. So we're sending the same bit pattern. We only have one wire, and we send those 8 bits one after another. Okay. So that's what happens. So normally in terms of hardware or manufacturing cost, the serial transmission is better because you only need one wire. So but with this design, we need to do some additional processing to be able to properly interpret these bit patterns. So we actually have under serial transmission, we have asynchronous, synchronous, and isochronous. So let's talk about synchronous transmission. So here, serial transmission, the timing of a signal is not important, and what it does is to use patterns or grouping of bit streams into bytes. So you don't just interpret one bit, so you group these bits, let's say, into 8 bits to form a byte, and that will be the interpretation. And within this, for example, a byte or 8 bits will be sandwiched between a start bit and a stop bit to indicate the start and end of a byte or 8 bits. So at the receiver end, it first has to detect the start bit, and once the start bit is detected, it will sample the line and get the remaining 8 bits and look for the stop bit, and then the receiver will interpret that as 1 byte or 8 bits. So there is no synchronization at the byte level. As long as the receiver can find the start bit, it's good to go. It can detect the succeeding 8 bits as data or information bits. But there's also a synchronization at the bit level. So let's take a look how it works. So we have the sender and the receiver. So the receiver will have to check for the start bit, and once the bit is detected, it will interpret, sample the remaining bits to interpret this as data or 1 character, and then it will look for the stop bits indicating the 1 character. And we may also have some gaps here. Okay, so that's example. So remember, for example, we have USB, okay, universal serial bus, right? So USB uses serial transmission, right, to transfer data. But this one is asynchronous, right? So the main idea here is to use start and stop bits to indicate, to mark the start and end of a character. Now in the synchronous transmission, the bit stream is combined into frames which may contain multiple bytes, right? So it's not just 8 bits. The unit is not just 8 bits. The smallest unit is the 8 bits. So the bits will be combined into a specific grouping or a group of bits that represent data, and it is the receiver that is responsible for decoding it, right? So actually this is the interpretation of this grouping of bits is done at the data link layer. Recall our discussion in the OSI TCP/IP model. So the grouping is actually called a frame, and it's not on a per character or per 8 bits basis. So the grouping can be something like this or something like this. Okay, so it is not fixed 8-bit grouping, and the interpretation is left to the data link layer. We'll talk about data link layer when we talk about HDLC, and it's going to discuss the different frames, and we're going to go back to this discussion on serial transmission, start and stop bits, etc. And the last one is isochronous transmission, which is used for multimedia data streaming. And there is a guarantee that the data will arrive at a fixed rate, so that there is no lag or jitter or whatever. So this is isochronous. Okay, so I guess this ends the chapter. So I hope in this chapter, after watching this chapter, you can now differentiate the data element from signal element. Easily done. Differentiate data rate from signal rate. Explain the relationship among data rate, signal rate, and effective bandwidth. Describe the properties of encoding techniques. Describe how bits are encoded using different techniques for digital transmission. Line encoding, block coding, scrambling, and describe how analog data are encoded using different techniques for digital transmission, Morse code modulation, delta modulation, as well as how these bits are transmitted over a link via the different transmission modes. Okay, so we'll stop here, and this is the end of chapter 4.